In this video, I'd like to give a brief introduction to my recent paper with a postdoc here at IPMU, Hao Zhang, which is about a certain Z3 valued topological term in heterotic string theory. So let me begin. So as you know, there are various types of string theory in 10 dimensions. You might have heard something called type 2A, type 2B, and something called heterotic strings. And there are two types of heterotic strings, which is associated to gauge groups SO32 or E8 times E8. And the paper is basically about this heterotic string of two types. So heterotic strings have the following bosonic fields in the massless sector. So you have the metric and the dilaton and the B field, which is a two-form field. So that if you take the extra derivative, you have a three-form field strength. And so this is the gravitational sector, and you have the corresponding fermions. And in addition to that, this theory has the gauge field, which I write as A, and corresponding fermions related by supersymmetry. So the distinction between two heterotic strings is whether this gauge field is in either SO32 or E8 times E8. And it is known that the interactions among the fields in the gravitational sector is constrained mostly by supersymmetry, and they are common to both SO32 and E8 times E8 heterotic string, except for the possible difference in topological terms. So the interactions can differ as far as the topological term is concerned. So, what are these topological terms? The prototypical example of the topological term in this case is the 3D Chern-Simons term. For simplicity, I just consider abelian gauge field U1. In that case, you can have a term of the form ADA, and the integrand is not quite gauge invariant, but its integral over a closed manifold can be made gauge invariant, but only when the coefficient in front of it is an integer. So this structure has appeared in many places in physics. So one example is that it describes an integer quantum Hall effect. So that's the 3D Chern-Simons term, and the coefficient is an integer. So the type of topological term discussed in the paper I'm talking about today is a 10-dimensional term with some coefficient, and in a very rough sense, it's a function of G and B. But the funny thing is that there's no differential form expression. So it's a very subtle type of term. And in addition to that, this value k is not only an integer, but it is modulo 3. So the value k being 0 and 3 are equivalent. And the main claim of the paper is that the two heterotic strings one of type SO32 and the other of type E8 times E8, have different topological terms, and the difference is given by one unit of this Z3 valued topological term. So, how do we determine it? There are a number of ways to do this. One method is to use a formula devised in a paper of mine. Co-authored with Mayuko Yamashita last May, and it's a differential geometric formula involving an eta invariant on a complicated space. So this is in some sense a very honest approach to the question, and with our postdoc Hao Jiang, we tried this for more than half a year on and off, but we didn't succeed because this formula is very complicated. So around November, if I remember correctly, we gave up on this approach and we moved to method B. And the method B uses more string theory. Because it's a string theory question, let's use string theory, that's the idea. And the basic idea, again, can be illustrated by going back to the case of 3D Chern-Simons. So, suppose you have a bulk 3D system with this ADA interaction here. So you can think of it as a quantum Hall effect material, and suppose it has a boundary here, and it is well known that such a boundary has a chiral edge current. And the point is that if the coefficient of the Chern-Simons term is k, then there are k units of the chiral edge current. And in terms of the anomaly of the boundary theory, the U1 symmetry in the boundary has k times the unit amount of anomaly. So this is called bulk boundary correspondence, or the anomaly inflow. So that's the 3D case. Instead, what we do is the following. So you want to think about 10D Z3 Chern-Simons like term, and so you have 10D spacetime, and I'm not going to consider a boundary here of codimension 1, but we rather consider a 6-dimensional subspace on which a kind of brain lives. So this is called an NS5 brain. So what happens is that there's an anomaly inflow from this Z3 Chern-Simons like term in the bulk 10 dimensions towards the world volume of this 6-dimensional theory on the NS5 brain. So the good thing about this approach is that the physics of NS5 brain have been studied quite well. So what we have on these NS5 brains and the amount of quote-unquote chiral edge current, or the anomaly on these 5 brains are known. So in the case of SO32, that was found around 1997, and for the case of E8 times E8, heterotic string, the anomaly on the NS5 brain was found in 2014 in a paper of mine with Omori and Shimizu, who were students of mine at that time. So the point is that we know the chiral edge current of this, we know the chiral edge current of that, so we know the difference, and you can trace it back, translate it back to the bulk information of the bulk term, and you can confirm that the difference of the Chern-Simons term in 10 dimensions is exactly 1 unit modulo 3. So that's the main conclusion of our paper. So you can ask the following question. So the basic data was given already in 10 years ago, right? So why are we doing this in 2024? So the question, the reason was the following. So first of all, the general formalism for mod Zn Chern-Simons like terms was established only in 2016 by Fried and Hopkins. And this was heavily influenced by the development of the theory of topological phases of matter in condensed matter physics, which started from around 2010 onward. So unless we had this general formalism, we couldn't even think of it understanding the 10-dimensional Z3 valued topological term. But once this is understood, the relevant computation, mathematical computation was already done a long time ago, because this general formalism uses something called Bordisms in mathematics. And the appropriate Bordism theory for heterotic strings is something like this. So mathematically, if you have a manifold, you can consider an orientation on it, right? And at the next step, you can consider introducing string structure. And then there's a natural sequences of structure on the manifolds. And there's the next step, which is called the string structure, even by mathematicians these days. But this was introduced long before string theory became known to mathematicians. And in the past, this was known as bracket H structure for some other reasons. And this was the Bordism theory for this was computed in 1971. So by just looking at this older paper and combining that with general formalism of Fried and Hopkins, you know that there can be a Z3 topological term in 10D. So you start to suspect that there can be a non-zero topological term in 10D. That's one influence. Another fact is as follows. So I've been studying the relation between string theory and some mathematical concept known as topological modular forms. So what happened is that in heterotic strings, you have a worksheet of the strings, right? So it's a two-dimensional theory. And given a two-dimensional theory, there's a mathematical proposal by Stoltz and Teitner from around 2010-ish, saying that given a worksheet theory, it should define an element in something called topological modular form. In particular, if you consider 10-dimensional heterotic strings itself, 10-dimensional heterotic strings should determine an object in the topological modular form of degree 32. If you look up the textbooks on these mathematical objects, which became widely available again from around 2010-ish, you learn that there's a unique subgroup of the form Z3. So, because we think that string theory is somehow magically knowledgeable about various mathematics, it is kind of natural to suspect that the difference between SO32 heterotic strings and E8 times E8 heterotic string should correspond to this particular Z3 element in the topological modular forms of degree 32. That's a natural guess. So that's why we started thinking about checking this correspondence, that this difference might correspond to this G3 element, and then that would correspond to the 10-dimensional topological term. So finally, let me give a slightly more detailed way how we computed this topological term. So what does this 10D topological term do? So I wasn't telling you exactly what this term is. For this purpose, consider SU2 bundles over S7, right? And if you consider it as a principal bundle, you have a fibration of SU2 over S7, and SU2 is just S3, right? So the total dimension is 3 plus 7, which is 10-dimensional. Exactly the dimension required for heterotic strings. And any SU2 bundles over S7 is obtained by gluing two trivial bundles around the equator, which is S6. Therefore, such bundles are characterized or classified by homotopy classes of maps from S6 to SU2. So the relevant homotopy group is S pi 6 on SU2, which is just S3, and this homotopy group turns out to be Z12. In heterotic string theory, we not only have the metric, which describes this geometry, but also the H field, which, as I said, is a three-form field, right? So we consider the situation where the flux of this H field through the fiber is exactly 1 unit. So you can consider this situation, and this Z3 topological term I've been talking about assigns this unit class complexified exponentiated action of exponential of 2 pi I over 3. So that's the definition of this very subtle Z3 valued topological term. And the computation of such terms is intimately related to the computation of global anomalies in 6D. And this is a very specialized subject, even within string theory or high energy physics in general. But somehow I liked it since when I was a grad student. So I first learned how to compute it in 2005 in a paper with Suzuki-kun, who was also a grad student in the same graduate school. And then after Fried and Hopkins came out, I worked with a former student of mine at the time on a Fried-Hopkins-like reformulation of this computation. In 2020 with Liku. And in the paper I'm talking about today, I needed to use the results I prepared unknowingly some time ago. So that's basically it. Let me summarize what I said. So in the paper I'm talking about today, we determined that the gravitational sector of two heterotic string theory, one with E8 times E8 gauge group and the other with SO32 gauge group, so the action in the gravitational sector are different by a Z3 valued topological term, which is a subtle Boldism version of Chen-Simon's term, which detects this S3 vibration over S7, which is a 10-dimensional manifold. And we did that by some indirect method using its relation to the anomaly polynomial of NS5 rings, which were known and determined before. And along the way, I was quite happy because I needed to use various papers of mine with either with my friend or my former students. I developed in 2005 with Suzuki-kun, 2020 with Lee-kun, 2014 with Omori-kun and Shimizu-kun. And I also needed to use my paper with Yamashita-san from last year. And finally, all of them were combined into a place with our postdoc here, Hao Jiang. So I was kind of very happy, which is why I'm making this video. Thank you for your attention.